Hi, folks. We're getting into it, starting the second law of thermodynamics. There's so many songs out there about entropy. I was trying to find one that I've never heard before, and I found this crazy pop song. I'm going to make you listen to like 10 seconds of it. That's what I came up with. You gotta love the internet. So, obviously, we're gonna start talking about entropy, okay, which is a huge connection in the second law of thermodynamics. Okay, so let's talk about that by first thinking about this bouncy ball example. So this is from the textbook, and I love this example as a description of entropy, spontaneity, and reversibility. All of these things are connected. Okay, so we start by imagining we have some bouncy ball, right? I can drop this bouncy ball, and we all know from our common experiences, it's just going to bounce. And on each bounce, it's going to bounce less and less and less until it hits the ground and rolls along the floor. So we don't have to have advanced degrees in science to know that as soon as I let that ball go, it is going to spontaneously bounce in the way that I just described. Okay? So what is it that's happening with this thing? Well, each time this ball strikes the surface, okay, it disperses some of its own kinetic energy into the ground. So really we could kind of, in some bigger way, say it's really dispersing heat into the ground. We probably wouldn't measure a whole lot of heat from just a single bouncy ball. But all the same, we recognize that heat and work are being exchanged in this process. Okay? And, you know, on the first bounce, we can conclude there is a lot of heat, or what I'll call thermal motion. So the disorderly motion of atoms as a result of energy dispersion. So that thermal motion gets dispersed into the ground, okay? And upon each bounce, there's less and less of that energy to be dispersed, okay? This is the road sign of a spontaneous change. Spontaneous changes are always accompanied by a dispersal of energy, okay? And so, for example, if we now imagine this bouncy ball that's finished, it's spontaneous bouncing, it's resting on the ground, and now we could ask ourselves, can that be reversed? Okay? And what would it take for that bouncy ball to spontaneously, reversibly start bouncing higher and higher and higher? Okay? So all of this thermal motion that was dispersed into the ground would have to now accumulate and concentrate at a single point. So we would have to like somehow allow the atoms in this floor to start vibrating, to start focusing that dispersed heat, okay? And start focusing it into that bouncy ball so it can start making the atoms in the bouncy ball vibrate to the point where they bounce, okay? And then on the second bounce, even more of those vibrations would have to be focused into a singular point to give it an even bigger bounce and an even bigger bounce, okay? I can say confidently that no one in the history of the universe has ever observed this to happen. That is a bold statement. You can spend the rest of your life trying to prove me wrong, but no one has ever observed a bouncy ball, or any other kind of ball for that matter, at rest spontaneously reaccumulate its spent kinetic energy to go back into bouncing in reverse. No one has ever witnessed this to happen, and thus we can conclude a deep connection between spontaneity and irreversible processes. Okay? So there is a dispersal of energy in all spontaneous processes, which has actually led to the very famous Lord Kelvin's statement of the second law, which states, no machine can exist which perfectly converts heat into work. So how do we connect these two ideas? This is a big connection, right? And if you're not seeing how those connect, then you're not alone. Okay, so let's think about this. Well, if we have a hot source, let's say some fire, whatever, a hot piece of metal, it doesn't matter. It's some object that is hot. It's hotter than this engine that it's trying to supply heat to. Therefore, we know from the 0th law of thermodynamics, when two objects are in contact at different temperature, heat will spontaneously flow from one, the hot object, to the other, the colder object. Okay, so this heat should flow spontaneously. Well, if it's spontaneous, there should be a dispersal of that heat. Okay? But what's happening in this picture here, all of this heat, which I'll remind you is thermal motion, so it's disorderly, it's chaotic, it's already dispersed. Okay? So now how are we going to take that dispersed heat and focus it back into work? Okay? We can't. It's this engine picture is the exact same as the bouncy ball. That's like saying we're going to take the dispersed heat in that ground and refocus it so that it gets converted perfectly into work. Such a machine does not exist, and so for this system to work, for this system to provide heat to an engine and do work, there must also be some loss of heat to the surroundings. Okay? So we can convert some of that heat into work. Otherwise, we wouldn't have things like engines to drive our cars or the original steam engines, right? Those wouldn't exist if heat couldn't be converted to work. However, heat cannot be converted into work perfectly. There has to be a dispersal or a loss of that heat as the thermal disorderly motion is being converted into orderly motion that we call work. Okay? So here we have another definition of the second law, and this is the more common definition, which states the entropy of an isolated system increases in the due course of a spontaneous change. So in other words, when something is proceeding spontaneously, entropy must increase. Now, we have to put a qualifier on that. We have to specifically talk about what entropy. So the entropy that has to increase is the total entropy. Sometimes this is referred to as the entropy of the universe. So the entropy of the universe increases in the due course of a spontaneous process. I like to use the word total much better because I think when we say universe, it gives us this idea that we're literally talking about like the whole universe, all the stars, all the planets, everything that ever was. And we could be. We very much could apply the second law of thermodynamics to the entire universe, but rarely do we do this in a chemistry lab. Okay? So I like to use total, and entropy total is in reference to the entropy of the system plus the entropy of the surroundings. Okay? And so the second law says total entropy. So I'll put a qualifier on there, and I'll just write tote. Total energy must increase in the due course of a spontaneous change. Okay? So S total, right, remember, which is going to be, so S total I can say is S final minus S initial, right, must be a positive quantity in a spontaneous process, okay? And so I'll read this other line that goes along with this that was kind of connected to the first slide I went through. Thermodynamically irreversible processes thermodynamically irreversible processes are spontaneous and hence must be accompanied by a dispersal of energy and increase in total entropy. Okay, so that's basically what we just said with not only that picture of the engine that cannot exist or the bouncy ball. Okay, if you have an irreversible process, it must have a dispersal of energy, which then, of course, will lead to an increase in total entropy. Okay, and so again, this is the same thing. I know it's hard to connect it, but this is literally the same thing as saying no machine can exist which perfectly converts heat into work. Okay, so moving along. Okay, so here is our thermodynamic definition of entropy. So this is our, for infinitesimally small changes, right? Our calculus-based definition. And of course, here is our definition for measurable changes. So when we can actually measure the change in the laboratory. So it says dq reversible. So the change in heat supplied reversibly divided by temperature by definition is ds. Okay, and that ds can become delta s by integrating over that expression. And of course, we recognize that entropy will be a state function. Heat is a path function. Okay, so what about entropy in the surroundings? Okay, so ds surroundings. And I could go on and I could expand on ds surroundings by putting dq surroundings reversible divided by the temperature surroundings. Okay. Well, as it turns out, in the surroundings, this isn't so important, whether it's supplied reversible or irreversible. And the reason for that is because the surroundings more often than not represent a gigantic reservoir of volume, temperature, work, heat, etc. Okay? The surroundings are almost always a humongous reservoir in comparison to the system. Okay? And so because of that, rarely does it matter if the surrounding entropy is brought about by reversible or irreversible change, as long as the second law is conserved. So what that means is when you're considering what's happening with the surroundings, whether it's reversible or irreversible, you still have to add that change to the change in the entropy of the system. And if that is a quantity greater than 0, then you know that entropy has increased. And you know that we can say that the system is being driven by an irreversible process, okay? The system. But all the same, if that process is to be spontaneous, it's the sum total of both the system and the surroundings that we have to consider, okay? And so we can simply write, by integrating along this thing, right? Integrate from initial to final, then we know the entropy of the surroundings is just the heat supplied to the surroundings divided by the temperature of the surroundings. And if we connect that even further, all right, we know that the change in heat of the surroundings is the opposite of the change in heat of the system. So for example, if it's exothermic as viewed by the system, then it's endothermic as viewed by the surroundings, or vice versa, right? So these are just connected by the opposite sign. And therefore, delta S of surroundings is going to be the negative Q of the system still divided by the temperature of the surroundings, okay? So for example, if we want to think about like a bigger picture, like a bigger universal picture thing, okay? So if we think about heat being transferred to planet Earth from the sun, right? So we would have S total, okay? And so we can write the delta S of the system as just Q system divided by T system, all right? But then now that's going to be negative delta Q excuse me. So if we were now thinking of the surroundings, we could say that that's negative Q. So I did that again. Negative Q system, that's what I'm trying to write. But now divided by T surroundings. Okay? So these quantities will not be equal to 0 if the two temperatures are different. Okay? And in the case of T surroundings being greater than T system, right? With, of course, that value of Q being the same. This is Q system, just one is negative, okay? This quantity will be much, much smaller, right? When the temperature of the surroundings is greater than the temperature of the system, we can say, we just proved that heat from the surroundings will spontaneously flow to the heat of the system, okay, when we have this situation, all right? And we can continue to play with these relationships in this way, right, to ask, is this process going to be spontaneous or is this process going to be non-spontaneous, okay? So this, you know, with this in mind here, I'll write, and as a conclusion, S total is greater than 0. And that's specifically, again, for, I gave you that example of like energy being transferred from the earth, from the sun to the earth, but just, you know, think of it as a more general example, right? Energy being transferred from a hot object to a cold object. If we define the hot object as the surroundings and the cold object as the system, we know this process will proceed spontaneously, okay? Moving forward, and again, that's just one example, all right? Okay, so, and then of course for units, right, we recognize that heat will have units of joules and temperature has units of Kelvin. So often we see entropy given in joules per Kelvin. Of course, we could, so that's for S. Of course, if we had molar entropy, joule per Kelvin per mole for the molar entropy. All right. Okay, moving right along. So now, taking advantage of that thermodynamic definition of entropy, let's come up with an expression for delta S of an ideal gas expanded isothermally in a reversible pathway. Right? So in other words, we have that definition, delta S equals I F dq reversible divided by T. And let's fill in stuff that we know. All right? Well, we know that isothermal, so anytime we see isothermal, what I want you to think of in your mind is delta T equals 0, which means delta U has to equal 0, which also means negative Q equals W, because we know delta U is Q plus W. So for all isothermal processes, work and heat are equal and opposite. Okay. And so now what about the expansion? How do we deal with that? Well, we know work is negative PDV. Okay. And if we go and take that integral, right, and we plug in an actual equation, PV equals nRT, we know then that the reversible work supplied is negative nRT natural log of VF over VI. Okay. So resultingly, the Q supplied reversibly has to be positive nRT natural log VF over VI, right? And so therefore, we know now that we can say, if I plug this in, and I know delta S is going to be the integral, which we technically already integrated that work expression. So now, right, because integrating dq just gives us, so from final to initial, right, just gives us Q reversible over T. Well, we integrated that already. We integrated it from V initial to V final to get the work, all right? And so the delta S then is just going to be Q divided by T. So that just results, so let's write that down. Q, oh, I did right there. Q reversible divided by T, okay? So now that just equals in R times natural log of VF over VI, okay? And so thus we can see here, we know R has units, so this would be the 8.314 joule per mole K, right? So when we multiply this by the total number of moles, we will have our total entropy. We'll have entropy in terms of joules per Kelvin. All right? So let's see here. Moving right along. So for adiabatic processes, so this is another scenario we talked about, right? We know in an adiabatic process, dq equals 0, so there's no transfer of heat. So then we can also say that Q surroundings equals 0. There's been no heat given, which means the delta S of the surroundings would also have to be equal to 0. Okay? And so therefore, S total is only going to be dependent upon the entropy of the system for an adiabatic process. And of course, if this is greater than 0, then it's spontaneous. Okay? And we have to be careful. Not every single process is spontaneous, right? So we can't just go and say that every single thing we can think of is spontaneous. But if we were to say we have an adiabatic process that proceeds spontaneously, then we know that that has to be driven entirely by the entropy changes in the system. Okay? So, moving along. So now we're going to kind of get into this weird land. You notice here now, all of a sudden I jump randomly to chapter 15.4 and 15.5. And I have these crazy things on here. I'm only going to talk about this very briefly. And in the learning goals, I only want you to be familiar with the following, not to like full, PhD thesis. But if you do want to read in more depth, I would suggest chapter section 15.4 and 15.5. And we've already looked at a little bit of 15 when we talked about partition functions. And hopefully you see that right there. That's somewhat familiar. But now I want to connect this idea that we talked about, partition functions, states, and entropy. Okay? And so we start by defining an ensemble. Okay? And an ensemble, I'm going to turn to a page in my book here just so I can read the correct definition, so I make sure I get it correct too. So an ensemble is a collection, and it can be dependent. It's a collection of states, okay? And that collection of states is dependent on what is being held constant, okay? So we have three different types of ensembles. There's the canonical, there's the microcanonical, and then there's the grand canonical. Everything that we will do in this class is related to the canonical ensemble, okay? So what is the canonical ensemble? So we start by saying we have some closed system. So that means and this is just with respect to the canonical, okay? Don't mix this up with microcanonical and grand canonical, okay? As it turns out, microcanonical is also closed, and I'll show you how we can tell in a moment, all right? So we start off with the closed system. I'll talk about this I in a moment. And in this closed system, we use the number of particles, or I'll just say number of things, that could be molecules, atoms, right? Electrons, whatever we want. It's the number of things, okay? And of course, we have V for, I ran out of room here, volume. And of course, T for temperature, okay? So this is what makes this a closed system, is that we are fixing the number of things in this box, okay? And so you notice here on the microcanonical, also closed system because the number of things in that box are fixed. But in the grand canonical, this is an open system, free to exchange heat and mass. Okay? So in the canonical system, it's a closed system with fixed composition, and we describe that system by use of the microstate. Okay? So in other words, the sum total of N, V, and T gives us the macro state. Okay? So the number of things, or the volume, or the temperature, that is what we refer to as the state. We've called this state function before, right? And I can call a state function P as a function of N, V, and T, right? And that will describe the macro state. Well, in this canonical ensemble, we say there is I number of these states, which we call microstates, and each one of those represents an equivalent way we can arrange this system and have the same energy. Okay? So I'll say that again. The microstate represents the number of unique ways we can arrange, in case of the canonical, the ways that we can arrange the number of particles, the volume, or the temperature, the number of ways we can do that and still result in the same energy. Okay? And as it turns out, that can be calculated with a partition function, and specifically we call this the canonical partition function, and it's the same partition function we've been looking at. So when we derived the Maxwell-Boltzmann distribution, that was derived from the canonical partition function, okay, which says the sum of all of these microstates is e to the negative beta times the total energy, or the energy of that state, I, where remember beta is 1 over k Boltzmann T. So we've already seen this partition function that we've already been looking at is what we call our canonical partition function, and it's specifically with respect to the macrostates, composition, volume, and temperature. Okay? I'll get into a little bit more detail on these microstates momentarily and what this all means. So now you can see with the microcanonical ensemble, it's the number of ways in which we can arrange number of particles, volume, but now instead of temperature, energy. Okay? And in the grand canonical, it's a wide open system, so there's no fixed number of particles. However, volume and temperature are fixed in the grand canonical, as well as this term mu that we call chemical potential. And I'm going to describe that as we'll talk more about chemical potential as we move forward. Okay? So that's all I really want to say about ensembles. For those of you that go on to graduate school and do, PChem, like you will take a statistical mechanics class and a statistical thermodynamics class. You will go into huge, hideous, disgusting detail on these partition functions and these various ensembles. I only just wanted to touch on this briefly and just make you somewhat familiar of what an ensemble is and how that leads to microstates. Okay, so let's look at maybe a little bit more straightforward way of talking about a microstate. So this is an example that I use in general chemistry. So suppose we have this four molecules in a 2-bulb flask. Okay, so we can say confidently here that N and V are fixed. So we're talking about 4 volumes. We're not going to change the volume of the flask. We're saying it's a 2-volume flask. And then also we're going to hold temperature constant. Okay, so we're working in the canonical ensemble. N, V, and T are all set to give us the macro state. Okay, and the macro state is just simply 4 molecules in a 2-bulb flask at some temperature. That's it. That's the macro state. What are the resulting number of microstates? Okay, well, if you start thinking about how we could arrange this, So we could have all 4 particles in the left bulb, and that would correspond to 1 microstate. That's one arrangement that doesn't affect the total energy of the system. But now if I start putting labels on those 4 molecules, I label them molecule A, B, C, and D. And I accept that, okay, well now one arrangement will be 3 molecules on the left and 1 molecule on the right. However, because I've labeled them, there's now 4 different ways that I could do that. For example, I could have only A on the right flask and B, D, and C on the left flask. I could now exchange A and B, or I could exchange B and C, or I could exchange D and C. That would give me 4 microstates, because none of those would directly change the energy of this system. All right? And if I kept going through all of these possibilities, I would have 1 plus 4 plus 6 plus 4 plus 1. So what is that? 5, 11, 16 microstates would result from this 1 macrostate. Okay? So we might imagine as we make this macrostate more complicated, so maybe instead of only 4 bulbs, what if it, or excuse me, instead of 4 molecules, what if it was 1 mole of molecules? We would have a hideous, disgusting number of microstates. Way too many to count. Absolutely way too many to count. So how could we then calculate those number of microstates? Well, one way would be to use the molecular partition function. Okay, we could do that. That partition function would help us sum all of those possible states. Another way would be to use the Boltzmann definition of entropy, which states S equals KB, K Boltzmann, times natural log, times W. So here in this equation, W is typically used to represent that number of microstates. Okay? So instead of counting those number of microstates, you could then determine the entropy instead, and that would tell you how many microstates you have. Okay? So of course, this would give us, K Boltzmann if we were talking about molecular units, right? Because we know K Boltzmann is joule per molecule per Kelvin. We know if we were talking about mole units, we could write S is R times natural log of the number of microstates. Okay? And really, instead of thinking about the number of microstates as this way of arranging things, a better way to think of that is the entropy. So we often think of entropy definition as like, the order or disorder, right? You commonly hear entropy as like a measure of chaos. Well, this is where that comes from. Because, right, with a large number of microstates, entropy will go up, and it will go up in this exponential way. Okay? Another way to think of this is, suppose we only had 1 microstate. Okay? Then what's our entropy? Natural log of 1, let's just double check in case we've all forgot. 1 natural log of 1 is 0, right? So if we only had 1 singular way to arrange our system, it has, by definition, no entropy. So start conceptualizing this thing between entropy and number of microstates. So entropy is not really a measure of chaos. It's really a measure of the number of ways we can arrange things without changing the energy. Okay? So, and now this other formula that I've put here, I'm not going to derive this, but this is how you could actually connect entropy as a function of temperature to that canonical, assuming I can spell, that canonical partition function. So that's what that Q is. So they're related, microstates and the partition functions. I'm not going to show how this is derived, and I'm not concerned with that. That you know how, you can look that up in chapter 15 if you're curious. But what this equation gives you is, so that's, internal energy right? Internal energy as a function of temperature. So whatever this temperature is, that temperature matches it. And as you might guess, at 0 Kelvin, this equation will just give you S of 0 is KB times natural log of Q, the partition function. So at T equals 0, I'm not going to show this, but we did talk about this earlier. Q is going to equal 1, okay? And so then we would arrive at this same conclusion, that at 0 Kelvin, we only have one singular way to arrange a system, and thus it's 0 entropy. Okay. So here is Boltzmann's tombstone. Famously, he has his equation, K log W. So, now we use the base E natural log. Here was the base 10. But very famous. It's really cool that he's got his equation on his tombstone right there. So really neat. Okay, continuing along. Okay. So, I'm going to end this lecture soon. Just a few more things to discuss. So I want to talk very briefly about entropy as a state function. So let me collect myself here. Okay. So what I'm showing you here is what we call a path. Okay. And so entropy along this path. So we remember that entropy is dq reversible divided by temperature, okay? And as it turns out, in proving this picture right here, if we were to integrate this picture, and I'm going to show you if we were to do the path integral, and the path integral means integrate along this closed loop path, okay, then we would get 0, which is just basically another way of saying if we integrated and started here and made it to the final state and then came back all the way around here, we would just have ended up where we started. And there would have been no change in entropy. Okay? Or in other words, the entropy of the final state would have been equal to the entropy of the initial state. Now the path, the amount of heat conducted might not be 0, right? Because we know Q is a path function. However, we do recognize in the state function, I'll just write delta S, that we're only interested in the final entropy and in the initial entropy. Okay? So, and then of course we can also conclude another bigger picture from this idea here is, and I have another definition here, and I'm not, another derivation, and I'm not going to go through it because we've kind of already proven that before. So I'll just do it briefly, but S total equals 0 for all reversible processes, okay? So that's kind of the conclusion I wanted to come to by doing a derivation, but I think more importantly, I would rather you just know conceptually delta S total equals 0 for all reversible processes. And the example of this with isothermal expansion comes from the fact that in isothermal expansion, delta T, that says delta F, delta T equals 0, delta U equals 0, negative Q equals positive W, okay? And if we keep going with this, we know work reversible, instead of deriving it, I'm just going to throw the equations up. Negative nRT, natural log over VF over VI. So then as a result, Q reversible has to be positive nRT, natural log VF over VI. Okay. We recognize that delta S surroundings equals Q of the surroundings divided by temperature, which is the same thing as saying negative Q reversible divided by temperature. So instead of saying reversible, I'll say system, just to not confuse that. System. Okay. Well, the Q of the system is right up here. Okay. which is just going to be divide this by T. So that's going to be negative NR natural log VF over VI. So that's our delta S for the surroundings. What's the delta S of the system? Well, the delta S of the system is just going to be equal and opposite of that because it's reversible. So delta S total is just NR natural log of VF over VI, but the surroundings is negative NR natural log of VF over VI, which equals 0. So I guess I still ended up doing that kind of short, very short derivation. But conceptually speaking, hopefully it makes good sense that delta S total has to be 0 for all reversible processes because you basically start and end in the same place. Delta S total is greater than 0 for all irreversible processes. Okay? Sorry, my handwriting is kind of going to shit today. Normally does on most days. Okay, so great. So that's where I'm going to end it for today. So just kind of introducing entropy. We're going to get more into the meat of this as we progress. I will see you later, folks.